makes
something
sense.
happen.
I just knew.
Yeah.
It was such a great
Like,
idea.
yeah.
Yeah. I do feel really bad that I forgot your blanket because I was really looking at it and I was like, no, I think you'll be okay today. She'll be fine.
Yeah, I'm pretty sure it's never ever been warm in this room.
It's a thought that counts.
It was actually hot yesterday in here. 'Cause I think they had the heater.
Where?
Just yesterday.
Yeah, because it was cold.
But then they decided, we don't need it today.
Well, I wasn't actually in this classroom, but I was down the hall. And
Yeah.
It was hot.
Ooh,
But
okay.
then I guess they decided it was good.
The math zone is sweltering.
Is it
Right
really?
now.
I haven't been there.
Well, there's probably too many people in it.
From 71 to finally 70.
No, I think I don't know, the air conditioning was on at some point and it
Right.
was
We're recording.
Oh, sorry.
We've been
You
recording
didn't
for
tell us.
45 seconds.
Oh.
So,
Oh,
That's not good.
okay. In case anybody has checked, I did not post notes for today. There aren't going to be notes for today because I didn't feel like actually latexing them up because, just because I'm over the semester. But I probably will have notes for upcoming sections, but all I have is I have a little bit from last notes that I haven't covered, so I'm going to do that first. And then I'm going to get into part of 6.2. Basically, it's going to be, I've done this a couple times already, like a diversion to do a linear algebra lesson for linear algebra that we're going to need for the rest of chapter 6. And so all I have is I just have some reminders. So whatever notes you take today, that will be all you need. That's why I didn't take anything up, because it wouldn't really, I didn't need it and you won't need it either. So
you always need notes. I always take notes.
yeah.
You don't know when you need it, but if you need it, then it should be there.
What?
Well,
You're so
no, it's for you.
philosophical.
No,
Oh,
Yes.
I think you always should take notes.
taking notes, yeah.
Right.
Yeah, because actually, like, what I'm going to do here, my notes for the rest of 5.3, they're pretty brief and maybe not clear enough, so I'm hoping what I do in the board will be clearer. Okay, so let's polish off 5.3. I stated the flow box theorem. Okay. All right. So the vector field x, that is C1, meaning it's continuously it's continuous first derivative, and we have a point C that is not a fixed point of x, and then vector field y. Is a constant vector field. It's just E1, first column of identity. Okay. And that means that, so when you have these conditions, what I stated last time was these vector fields x and y are differentiably equivalent. For little x near C and y near 0. Okay, but so now I can get a little more specific about this, what I mean by differentially equivalent. And we talked about differential equivalence before, but to refresh your memory, what that means is there exists diffeomorphism, the only morphism we'll be dealing with today. I'll call big F, where the push forward of x through F is y. Okay, so that's what we mean by two vector fields being differentially equivalent if there's a push forward map that relates the two. So you might think, if we're going to prove this, so that's basically going to go through the main ideas of a proof here. We would ought to construct F, or get some idea what F is, but we're actually not going to do that. We're going to go the opposite way. We're going to find a diffeomorphism. You really need to make these words shorter. To find a diffeomorphism G that goes the other way. So the push forward of y through G is x. And if we could find that, then our push forward F is going to be G inverse, because the diffeomorphism is 1 to 1 and onto, therefore it has an inverse. So we can just find F's inverse and just make sure that it really is a diffeomorphism so that we can invert. Okay.
What's that little thing at that very first line? Is where you put it.
I'm sorry, what?
Okay, where it says the vector field x and c. What?
C1.
That's a 1. Okay.
Yeah. And it's continuously differentiable.
Okay.
Yes. All right. So how are we going to get this G? It turns out to be easier than you might think. So I'm going to find a vector v1 to be x of c. And what's very important here, this is why it's important that c is not a fixed point of big X. So then we can be sure that this vector is non-zero. Okay. And then what I'm going to do is, and maybe this is one reason why I wanted to do this proof, because it's largely a linear algebra exercise. I'm going to define this subspace V be the orthogonal complement of V1. Actually, in order to be more precise, I shouldn't say V1. So basically, this will be between what I'm doing now and what I'm doing later. It's be hodgepodge linear algebra terms that you may have learned at one time and have since forgotten. Of span V1. And by span of a vector or set of vectors is a set of all linear combinations of those vectors. Now in this case we only have one vector, so span of V1 is just all scalar multiples of V1. So if you take a vector and you consider all scalar multiples, the span of it, that's a subspace of Rn. It's a one-dimensional subspace of Rn because we only have one vector. So V is the orthogonal complement of this subspace. Now what does that mean? If you have a subspace and you take its orthogonal complement, well, does anyone know what the orthogonal complement means? Not even Abdullah?
You told us that in 610.
I did.
Well,
See, well, you two were in 610.
It sounds familiar.
It
Okay.
does, and I hated that stuff, so I don't know.
Okay.
orthogonal complement. So,
It
or
confused the crap out
orthogonal
of me.
means if you take the dot product, you get 0.
Right. Yeah, this means to be orthogonal. So the orthogonal complement of a subspace would be. It's not ringing a bell.
Oh, it has to do with like the rank and the null space thing, right? No, wrong thing.
Well, it kind of relates to that. But
Okay, if something
I
is
don't know.
orthogonal,
This free updation work. I'm ticked.
and if it's complement, it would be
Ugh.
parallel
no.
itself.
Okay.
No?
All right. The orthogonal complement of a subspace. So it's equal to the set of all vectors in Rn such
That are
that
not in the-
V is perpendicular orthogonal to V1. Yes, so the orthogonal complement of a subspace is a set of all vectors that are orthogonal to every vector in that subspace.
Ah.
Yeah, so basically,
Crap.
okay. Now,
that. But why would that be a complement then?
because basically what you're doing is you're taking Rn and you're partitioning it into two subspaces.
Okay.
Is
Like-
that supposed to be a big V1 in the span, or is that a little V?
These are all little
No, where that
Vs.
says span of V1.
That's a little V.
Little V.
Yeah, the only big V I have is
Is
for
that-
subspace. Yeah.
Okay, that's
Okay. So Rn is an n-dimensional subspace, and one part of it is span of V1. The other part, the other n minus 1 dimensions, are sort of all vectors that are orthogonal to V1. So, so since this has dimension n minus 1, good, because a subspace and its orthogonal complement together have to have dimension n to take up all space. So I can define it to be the span of vectors v2, v3, up to vn. So all of these vectors, dot product with v1, is going to be 0. All these vectors are orthogonal to v1, and therefore any linear combination of them would be 2. Okay. So these guys, v2 to vn, form a basis for the orthogonal complement. So that what that also means is because v1's orthogonal all of them, I could say that the vectors v1, v2 up to vn form a basis for Rn, which I'm going to need later. Because if n vectors are linearly independent, and they span the entire space Rn. Okay. So I'm going to use all of these vectors in order to define what my push forward G is. All right. Now, so here's the definition of my push forward G. Now, okay. So I define G is basically going to be a function from Rn to Rn. So my parameters are going to be T. So T represents time as always. And then constants A2, A3, up to AN. So, okay. And what this function is going to do is it's going to use the flow map of the vector field X. So the phi sub t of this vector, C plus. So my constants here are going to multiply the corresponding vectors. Okay. Now, flow map was covered a while ago. That's actually when Dr. Tian was subbing. So, to refresh your memory as to what this means, this is the solution curve of your original system, big X, at time t, so the time is this subscript here, and the initial data is actually whatever's the argument to the flow map. So in other words, if you have a solution curve that starts at this point, you take that and you evolve along the solution curve to time t. That's what this whole expression means. Okay. Now, I'm going to define a point x to be c plus this same expression here. So actually x is going to be this whole thing. And the n. All right, now the reason why I'm doing this is x is therefore in a neighborhood of c for these constants near 0. Because the thing is, I want x to be near c, and I'm dealing with y values that are near 0. Okay. All right. So I want to show that if I take my push forward map G star of y, and I want to evaluate it at x, for x near c, then I should get big X of little x. So that will show what I'm looking for. That the push forward of big Y is big X, for as long as x is sufficiently near c. Okay. All right. So I'll just try working out what this is. So first I need to recall the definition of push forward. So the definition is, let's recall that here, it's going to be G prime of G inverse of x, or whatever x I'm plugging in, times big Y, which is what I'm taking the push forward of G inverse of x. So that's just a definition of push forward from earlier in the chapter. All right. Now this is why it was such a good idea to make a Flohbach's theorem relate x, big X, to a vector field big Y, but it's such a simple form. Because this right here, that's just E1. So when you take, now G prime is a Jacobian matrix. If you multiply a Jacobian matrix, if you multiply any matrix by E1, what does that do? Also a 610 topic.
Only take the first row,
No,
column.
column. Yeah, multiply on the right to take a column.
Yeah, because
Multiply.
So you take the column.
Multiply on the left to take a row. Okay, so this is the first column of my Jacobian matrix. But if you keep in mind what a Jacobian matrix is, I'll write it as columns. So G prime is a function of y. Now my y value, so you can think of this as what we're using for y values. They have coordinates t and then a2, a3 up to an. So my Jacobian matrix would be partial of derivative of g with respect to t as the first column, partial g with respect to a2, a3, all the way up to partial g with respect to an, evaluated at g inverse of x. So we're only taking the first column of this, so it's just going to be dg dt. So the dt at, now the thing is, okay. Now, what is, well, okay, so this is G inverse of this x. So it's C plus A2, B2, etc. up to AN, BN. Okay. So what I need to do now is I need to take this x and I need to, what does G inverse do? G inverse takes in an x and gives you back a y. I need to know what is the y that corresponds to this x. Well, okay. So the thing is, this is the flow at time t with initial data x. But this whole thing is equal to x, so this inside here is x. But this is equal to x at which time t? I need to know the t value. So if this whole expression, phi t of x, is equal to x, but when does that happen? What time?
T equals 0.
Yeah, t equals 0 because x is the initial data. So because that's when, I'm running out of room here, but phi t of x equals x when t is 0 because you're at your initial point on your curve. So, okay. So that means that my t value will be 0, and then my other parameters will just be these constants, a2 up to an. Okay, so all of this is my push forward of y evaluated at x. So where I'm at now is dg dt, and I now know what g inverse of x is. It's going to be 0, and then a2, a3, up to an. Okay, I know all this stuff's kind of weird, but is there any questions so far? Of,
Yeah, so I got that part, but T equals 0, which makes is the C equal to 0?
no, C is still C.
So what do you
Because what happens is, if I plug in
Okay,
t equals 0,
G inverse of C is T and T equals 0.
sorry, say again?
G inverse of C is T.
T inverse?
G inverse.
G inverse.
Yeah,
Yeah, G inverse, well, okay, suppose we only had C here.
right.
If this whole thing was equal to C, then we'd have G, so G inverse of C would be 0, 0, 0, 0, 0, 0.
Right.
Yeah, which is actually going to help us later. So since x is prescribed to be of this form, if g of something is equal to just plain x, so in other words, the flow map isn't doing anything, you can just take it out. The only time that happens is when phi of x equals x, which is when t equals 0.
Right.
Okay, so so whatever constants you're multiplying these vectors, those are the other parameters. So
Yeah.
yeah, so all of this here is G inverse of x, and the reason why is G of 0, A2 up to AN is flow to times 0 of x. That's just x. Okay. So really all I'm doing is I'm taking this relationship and going backwards. Okay. Now, Okay. But now I just need to take into account what is G. I define over there, G is the flow. So G, so I'm taking derivative effective time of the flow of, okay.
C plus H2V.
Well, I'm not sure if I want to write that at that exact point. Okay. All right, so G of Y evaluated at Y equal 0, A2, up to AN. So I want to defer evaluation until I've carried out all the differentiation. Okay. All right. Now, here's the thing though. Phi, the flow map, describes a solution curve. So this is solution of x prime is equal to big X of little x. So if I take the time derivative of the solution, what does that give me?
Like you were saying alpha prime T.
Yeah, it is alpha prime of t. Yeah, you can think of this as, yeah, being like an alpha of t, but now I'm taking alpha prime of t. If I take a time derivative of a solution of this system, what is that also equal to?
So your beta.
No?
It's like x of like alpha comma x. Like it used to be that. Like it's
Okay, I think you might have it, but okay.
x
So in other words,
alpha T of x. So
yeah. So
yeah, x of phi of T.
big X, yeah,
Big of yeah.
yeah. So it is big X of
That flow.
this flow.
Yeah.
Pt of okay. Well, actually, okay. Wait, this is written wrong because t is a parameter of y, so really this is g of y. But y equals all this, and that's so what it gives me is x of g of y, which is big X of the flow at time 0 of okay. All right. Oh, no, I shouldn't write it like that. This. Okay. So in other words, I've taken all these coordinates of y and I've plugged them into here, into the definition of g.
So you didn't need phi in there because phi was a parameter of it.
And because
Phi was already in one. So you just can't have
yeah, because 'cause it doesn't make sense to say phi of y.
Right.
Okay. Okay. So G normally gives me the flow, but now it's giving me the flow at 0. But the thing is, the flow at time 0 is whatever you're taking the flow of. So it's just big X of what's inside here. Okay. But that's vector here, that's little x. And that's what I was trying to show. Okay. All right, so to recap, what's going on here is I'm using a definition of push forward, but y is just the first column. It's E1. So I'm just taking the first column of a Jacobian. It wasn't the first column of Jacobian, but it's partial derivative of g with respect to your first variable, which in this case is t. But because big G is a flow, taking the derivative with respect to time of a flow just takes the flow and plugs it into your vector field. So that's the key thing right here, that by defining G to be a flow, that's the only way to get to here. And because I'm taking the flow at time 0, this flow function itself goes away. Just because, again, phi0 of x equals x. So that tosses that out. So back down here. And because the push forward of y is equal to big X, so I can say that in general, so I have that. So I've defined a push forward of y that gives me x. But we're not done. We're almost done. And this is a key step right here. But there's one more thing I need. Because what I really wanted is f. I need a diffeomorphism so I can take a push forward of x and give me y. So now the thing is, I'm not yet sure that I'm allowed to go backwards. I need to make sure that this mapping, this G, is actually invertible. So we need to show that G prime at the origin is actually invertible. Because if we can show that, that means that the push forward map is invertible, and f, which is G inverse, exists. Near C, which is G of 0. Okay. So, because this is a result of the inverse function theorem. So, inverse function theorem is a very important result of calculus, which shows that if you have a function that maps Rn to Rn, and its Jacobian matrix is invertible at a point, that means that the function itself is invertible near that point. Okay. All right, so what is this Jacobian at 0, 0, 0? Well, if we recall what G is, it's, all right, so it takes parameters t, a2 up to an, which is phi t of c plus a2, v2 up to an, bn. All right, now, so the thing is, we need to take partial derivatives of all of these. So, partial of G with respect to one of these A parameters, at the origin, so everything is equal to 0. Well, that's going to be the partial derivative with respect to AI of this evaluated at at 0. So the thing is, because t is equal to 0,
Yeah.
that means that the flow part goes away.
So it'll just be VI.
Yes. Because it's a linear function of all these a's. So you just take whatever's multiplying the appropriate a, and that's going to be di. And that's for I equals 2 up to n. Okay. And then, so that fills in most of the Jacobian right there. What about differentiating with respect to t? Well, the partial derivative of g with respect to t at the origin. Well, we're taking a time derivative of a flow map. We did that earlier. That's going to be plugging into big X. So it's going to be big X of all this at the origin. So what that means is all of these a's are going to be 0. So what's left? That's going to be x of c. But what is x of c? How did I define that?
0.
No.
Oh, not 0.
Yeah.
It was.
I call it v1.
Oh, yeah. Yeah.
Okay. Wow, I'm using a lot more time for this than I expected. Oh, darn. Okay. So, and it sucks that I've filled the whole board because I only have a tiny little bit left. So, my board's going to suck, but at least your notes will be organized.
Those say the little subscripts on those, the little version, those are zeros, right?
These are all zeros.
Okay. I wasn't sure.
Okay.
Sorry.
All right. So what happens here is, so my final line is my Jacobian at the origin is just v1, v2 up to vn. So we constructed all these vectors this way in order to make this happen. Because what do we know about v1, v2 up to vn as a set?
They form a basis.
They form a basis. So if you have n linearly independent columns in a matrix, what do we know about the matrix?
Linear.
It's invertible. Yeah. So that means that F inverse exists near C, which is G of 0. All right. So because we have
You mean G inverse?
yes, so, or to be more complete, F equals G inverse exists here, there. So that means we have a diffeomorphism, big F, because G is invertible near 0, F is invertible near C, and then we can define a push forward from F that pushes X to Y, just as G pushes forward Y to X. And the dang Flohbach's theorem proof is complete. I think it only occupied just about a room in my notes, but I wanted to be more detailed here. Questions? Well, the thing is, you didn't have analysis to fry your brains, so it was up to me.
How kind of you.
Yeah, because you can't let a day go by without that happening. So, well, at least it's Wednesday. All right. Okay, so during what time is left, so that's the end of chapter 5. Chapter 6 is all about stability for nonlinear systems. And I'll have more to say about that precisely next week, but the basic idea behind stability is if you have a fixed point or a limit cycle, something like that, when are they stable? Which means, when do solutions stay near it or are attracted to it? Or do solutions gravitate away from it? That's what, because we've talked about fixed points being stable or unstable before, but now in this chapter we'll be able to say more about it, and we can use linear algebraic methods to determine whether fixed points of higher dimensional systems are stable or unstable. And this is actually important, even though it's not discussed in the text. This is important for instance, numerical solutions, because if you're trying to solve a system of equations numerically, there's going to be round-off error. So if you're dealing with an unstable fixed point that drives solutions away from it, and you have some error, that means the lower solution you compute can be so far off as to be useless. But if you're dealing with a stable system, then it's okay. All right. But in order to analyze stability of fixed points and limit cycles and so forth, we need a little more material about computing matrix exponentials. You've done some of this in the chapter 4 homework, but there's some more details we need now. Plus, these are just good linear algebraic things to know. All right, and okay, see how far we get. Now, I've talked about the Jordan form before, but we're going to modify this a little bit to talk about the account for a case where you have complex eigenvalues. So, just for reference, you want to look in the textbook later and doing material from section 6.2. 6.1 just gets into definitions of stability, and I'm just going to get into that next week. In fact, I'm not even giving problems from 6.1. Okay. Well, I figure if I'm running out of steam, chances are you guys are too.
That means we are.
And we're already.
That means we already.
Exactly.
Well, yeah. Okay, so matrix A is this form x, j, x inverse. J is the Jordan form, and J has this form, Jordan blocks. Okay. Now, at this point, I don't care about whether anything in here is real or complex. We're just going to deal with it. Where each Jordan block has this form, has an eigenvalue, all along a diagonal, and then ones above it. And it may be a 1-by-1 block that has just the eigenvalue. And the way this is normally defined, lambda can be real or complex. But we try to avoid dealing with complex numbers as much as possible. So what we better do is, even if a matrix A is real, even though we have complex eigenvalues, we'd like to have a Jordan form that consists of only real numbers in spite of those complex eigenvalues. So all it takes is a slight modification of this. So I'm going to assume that A has R real eigenvalues and P pairs of complex eigenvalues. Hold on, I need to add more notation. Real eigenvalues I'll call lambda 1, lambda 2, up to lambda r. And then P pairs of complex eigenvalues are complex conjugates. AI plus IBI up to B. Oh, plus or minus. To account for it must be complex conjugate pairs. Okay, so what that means is R plus 2P is equal to N, where N is where A overall is n by n. Okay, so so now we can describe the Jordan form. So we'll have okay. All right, so we have all these Jordan blocks, and then, but it could be of whatever size. And then we have complex okay, actually, I use lambda 1. Hold on. I need to do a notation check. My book's in my office. Okay, so maybe we should have checked that from the song check after one. Oh well. Dang it. Okay. Alright. Okay, yeah, because you have to account for multiplicity. So actually I didn't need the book, but I want to be consistent. I'll define all this momentarily. Okay. As far as how I define this, okay. Okay. Now, each of these Jordan blocks could have a different size. So what happens is K1 up to KR, these numbers here, and also M1 up to MP, these are what are called geometric multiplicities. No, that's not true. They're algebraic multiplicities. Okay. Now, because when I described Jordan form some time ago, the number of Jordan blocks for a particular eigenvalue is a geometric multiplicity. How many actual blocks you have. But the size of a blocks is indicative of algebraic multiplicity, because if you have a repeated eigenvalue, let's suppose an eigenvalue is repeated 5 times, and there's only one eigenvector for an eigenvalue, the rest are generalized, then you're going to have a Jordan block of size 5 by 5. So the subscripts here for Vijay's indicate the size of a block. And the same thing for these guys, because here we have 2 eigenvalues, 2 complex eigenvalues that are repeated M1, M2, etc. number of times. The 2 is in here because there are 2 eigenvalues, so the size of a block is going to double. Okay, so now I can go ahead and describe what do each of these kinds of blocks for real and complex cases look like. Okay, so
You know,
chalk?
like when you rub it, the chalk is like smoothly falling down.
Oh,
like snow. Yeah.
wow.
Falling down the board.
Oh, creepy. All right. So if I have a Jordan block of a certain size for a certain eigenvalue, it's going to be k by k. It's going to have landed down a diagonal, and one's up above it. But the point is, it's going to be a k by k matrix. Okay. Now, what about the complex cases? Because we want to have real entries, even though the eigenvalues are complex. So this will have is instead of being a bidiagonal matrix like this, it's actually going to be a block bidiagonal matrix. Okay. And do you know how to find that here? Oh. Okay, so more crazy notation. So I'm going to find a matrix CAB that's going to go all the way down a diagonal. And C of AB with no subscript. A is the real part that goes in the diagonal. B is the imaginary part, so B and minus B go on the off-diagonal entries. So this has eigenvalues A plus or minus BI. We've seen this before. But then, up above, we have 2 by 2 identity matrices above it. And it's going to be, the size of the matrix is going to be 2m by 2m, but it's going to be m by m blocks, but each block is 2 by 2, thus accounting for the overall size. So, as an example, C6 of 5 and 4 is going to be a 6 by 6 matrix. So we'll have 3 by 3 blocks. So we'll have a block 5, 4, minus 4, 5, 5, 4, minus 4, 5, 5, 4, minus 4, 5. And then we're going to have a 2 by 2 identity block up here and up here. And then, so I'll partition these off. So you can see the 3 by 3 block structure. And then all other blocks are 0. So that's what these complex Jordan blocks look like. So even though they correspond to complex eigenvalues, in this case, lambda is 5 plus or minus 4i, that are repeated 3 times each. So 5 plus 4i is algebraic multiplicity 3, and 5 minus 4i is algebraic multiplicity 3. That this complex Jordan block still has all real entries at least. Okay. Now, so the first thing is, because we want to be able to compute exponentials of matrices such as these. So, we're talking about matrices of any kind that have a block diagonal structure. It turns out they're easy to multiply and easy to exponentiate. So this is something, actually, one of the homework problems from chapter 6 is to prove this, but it's probably not something that's hard to convince yourself of. If you have two matrices of the same block diagonal structure, so we have blocks A1, A2, A(n) down a diagonal, and then blocks down diagonal for this matrix too, zeros everywhere else. If you go ahead and multiply these things, that amounts to nothing more than just multiplying corresponding blocks. Okay. Now this is easiest to see if the blocks are just 1 by 1, they're just numbers. You could, that's what it would not be hard to prove, but it turns out that it doesn't matter what the size of these blocks are, even when they're matrices, it still works. But you have to respect the order. Right? A's before B's, because this A's before B's here has to stay the same here. So watch your order. But otherwise, it's all good. You can go ahead and multiply them. And as a consequence of this, because the same thing will be true for adding. That's a lot easier to see. Then you can just go ahead and add corresponding blocks. So A1 plus B1, A plus B2, etc. Or A1 plus B1, A2 plus B2, and so forth. So if you put those two together, multiplying and adding, that means that the exponential of a block diagonal matrix is just, you just exponentiate each individual block and put that along the diagonal. Okay. So for exponentiating Jordan block, what you can do is you can just, Jordan canonical form, you can just exponentiate each individual Jordan block and independently of the others. So that's one of the reasons why we like the Jordan form, because we want to exponentiate all of A, which is a general matrix. But exponentiating A, we can just exponentiate the Jordan form. So e to the AT is x e to the jt x inverse, but now that's going to be x e to the j1 down to e to the jp x inverse. So now we've drastically reduced the size and complexity of our exponentiation problem. Okay, so that's one key result that we need. And here's another that is also going to help us. For a task of exponentiating each of these individual Jordan blocks, that if you have the exponential of a sum of matrices, now when you're exponentiating numbers, you're accustomed to this. You can write it as this, e to the a times e to the b. However, you cannot do that in general for matrices. This is only valid if A and B commute with one another. In other words, AB is equal to BA. So this lets you cut down the size of the exponentiating problem even further. Because we can express any of these Jordan blocks, real or complex, as a sum of matrices that commute. Okay. All right, I think I can do this for at least the real case. Hopefully I can, before time is up.
What happens if they don't commute?
Oh, then you just can't use that. Which is quite a bummer. There are cases where I wanted to do something like that, but like, no, if you don't commute, you're out of luck. And unfortunately, there's no simple generalization. That you just have to exponentiate the sum as a whole. Okay, so we'll spend the rest of the time talking about a real case. So we can say that J, size K of an eigenvalue lambda, which has this form, lambda, 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 and then ones above, we can write that as a sum called lambda times the identity of size K by K plus this matrix n sub K. And n sub K is, it just has ones on the super diagonal and zeros everywhere else. Okay. Now, so you can think of this as, from what I was doing a second ago, as your A and your B. Well, it's actually really easy to see in this case that these two matrices commute. Now, that's not easy to determine in general, but why is it easy to see in this case?
Well, that's one is the identity
Yeah, because one of the matrices involves the identity. Every matrix commutes with identity. So it doesn't even take any special knowledge of this, because nk identity equals identity times nk, which is just nk. And the fact that we're multiplying by lambda is not going to change that. So, what that means is the exponential of this Jordan block is the same as the exponential of lambda k by k identity times the exponential of nk. So you can treat the two separately. Okay. Now, let's take a look at the first one. E to the lambda identity k by k. We'll just use a Taylor series definition of exponential. That's going to be lambda identity k by k to the j power over j factorial. Well, that's the same as lambda to the j over j factorial times the identity matrix to the j power. But any power of identity is identity. So this is identity k by k, and then you have all this. But that summation, what is that? Yeah, it's just e to the lambda. So it's just e to the lambda, the number, so it's exponenting a number, times the k by k identity. So that means my exponential, my Jordan block, is nothing more than e to the lambda times e to this nk matrix. So that's the only thing I have to figure out now. Okay. So something we ought to know about this matrix, n sub k. It has a name term for it. It's called a nilpotent matrix. Does anyone recall from any linear algebra class what a nilpotent matrix is? What? Oh, really? Okay.
I've heard the word that one.
All right.
Fluid?
So it doesn't do anything.
Well, it actually doesn't.
Nil means zero.
Yeah, and that's important because so nilpotent matrix is
Potent means strong.
yeah. So n. Yes, it's so strength 0. So n is nilpotent if n to the j is equal to 0, but n itself is for some j. But n itself is, so it's a non-zero matrix. If you raise it to a high enough power, you get the zero matrix. And one consequence of that is all the eigenvalues have to be 0. So yeah, because you can have a matrix that's all 0 eigenvalues, but the matrix itself is non-zero. So that's what a nilpotent matrix is. So you can actually so it turns out that, in this case, matrix defined like this, nk raised to the k power is actually the 0 matrix. Now, the thing is, in order to be able to exponentiate it, we need to know something about what the powers look like before it becomes 0. So the fact that it's going to be 0, that makes things a lot easier for exponentiating, because you could use a Taylor series, but it's not an infinite series. It's going to stop at some point. Because you're taking powers of matrix and you're just going to have a few terms and you're done. Okay, but still, we need to know what the powers look like. So, okay, almost done, I swear. So if nk is equal to 1 on a superdiagonal, what happens when you square it? I won't go through the whole thing, you can try it yourself on a simple example. What it does is, it takes these ones and it just shifts them to the right. So the main diagonal is still 0, the super diagonal is now 0, and you have ones here. And that's what happens as you keep taking a matrix to a new power. It just keeps shifting those ones. And at some point, each time you have fewer and fewer ones. So at some point you just fall off the edge, and you're left with nothing. In fact, this is done in the book for a 4x4 case. So you raise it to the third power, and you just have a single one sitting there. You multiply it by n one more time, all gone. So now how do we exponentiate it? So e to the nk uses Taylor series definition, except we're going to stop at term number k, because all other terms after that are going to be 0 anyway. So it's going to be, well actually, we don't want just e to the a, we want e to the a t. So I'll throw a t in here. So it's nkt raised to the j power over j factorial. Okay, so so what this is going to be is, for first term, you're just going to get identity. Then for second term, you're going to get t times nk to the first power. And then you're going to have t squared over 2 nk squared, and so forth. All the way up to, actually, I could stop at k minus 1.
K 0, right?
Yeah, so I have t to the k minus 1 over k minus 1 factorial, nk to the k minus 1, and that's it. Those are all the terms I get. Now, every time I take a new power of nk, my non-zero entries shift to a new diagonal. So what this means is, I'm going to have ones on the diagonal from the identity term. Then I'm going to have t's along the super diagonal from the second term. And then t squared over 2, t cubed over 6, and so forth. And in the very upper right corner, I'm going to have t to the k minus 1 over k minus 1 factorial. Okay, so that's what the exponentiation of this matrix exponential of this nilpotent matrix looks like when you throw a t in there. So now I can finally describe, well, at that point, there's almost nothing left to do. So the exponential of an entire real Jordan block times t of size k by k, so this is my final result for the day, is this e to the lambda t, that's just a number sitting on the outside, times all this. And so that's the general formula for the matrix exponential of a real Jordan block. Now, actually, this would apply just as well if lambda happened to be a complex eigenvalue, but then you'd have complex values in your matrix exponential. So, okay, so that's all I'm going to do today. And then on Monday, we will finish this up by doing a similar thing for complex Jordan blocks and see how we exponentiate those. Okay, oh, only 1 minute late, but You guys, okay, I guess you guys have class, but you're not gonna go.
I love how you know that.
Oh, yeah.
That
And
we
now,
all talk to you and we're just like, we're not going.
yeah, and now it's on YouTube.
Yeah, with my hand on it.
Yeah, but
I won't.
well, it's not like anybody else is gonna watch.